All right, everyone, welcome to part 2 of the collision video. So a 0.05 kilogram magnetic ball is moving to the right with a velocity of 3 meters per second. A 0.05 kilogram magnetic ball is moving to the left with a velocity of 4.5 meters per second. These two balls collide head-on. What is the final velocity of the magnetic balls? So this is assuming that they are sticking together and then moving as one, and we want to know what the final velocity of these two magnetic balls that stick together is. Okay, so let's start by identifying what we have in the problem. So M1 is equal to 0.05 kilograms, and it's moving to the right with a velocity of 3 meters per second. So V1 is equal to 3 meters per second. M2 is also equal to 0.05 kilograms. And this magnetic ball is moving to the left, so this is going to be our negative side, and this is going to be negative 4.5 meters per second. These two balls collide head-on. What is the final velocity of the magnetic balls? So we want to know what this final velocity is, and that's because this is a inelastic collision. Okay, so inelastic collision. So our equation for this is m1v1 plus m2v2 is equal to our masses combined times a final velocity. Alright, so let's plug in our information here. So we have 0.05 times 3 plus 0.05 times negative 4.5. And this is the collision point, this equal sign, and then our masses are going to combine, so 0.5 plus 0.5. And then a final velocity is going to result because of this collision. All right, so let's do the math, break out those calculators. So 0.05 times 3, and then 0.05 times negative 4.5. So if we added those two together, we're going to get a final momentum of negative 0.75 kilogram meters per second. And this is going to be equal to 0.05 plus 0.05. So 0.1 kilograms times VF. So our velocity final for this is going to be negative 0.075 divided by 0.1. So our final velocity for our objects here is negative 0.75 meters per second. Alright, so this is another example of an elastic collision. Elastic. So Homer shoots off a model rocket at 4.0 kilograms from his launch pad. The rocket is shooting 0.05 kilograms of burned fuel from its exhaust at an average velocity of 625 meters per second. What is the velocity of Homer's rocket after the fuel has burned? So we have this model rocket here. Alright, and we're going to shoot it off from this launch pad. So initially, V0 is equal to 0 meters per second. Whether it's for the fuel or whether it's for the rocket itself, it's going to be 0 meters per second here. Alright, so let's identify what we're given in the problem. So M1 is equal to 4 kilograms. M2 is the fuel here, which is 0.05 kilograms. And our velocities for each initially is 0 meters per second. And I'll just put V2 is also 0 meters per second. All right, I recognize that this can be kind of confusing, so I'm going to go ahead and put a 1 there. All right. And after the rocket is launched, the fuel has a final velocity of 625 meters per second. And we want to know what's the velocity of Homer's rocket after the fuel has burned. So we want to know the final velocity of Homer's rocket. And again, just to reiterate, this is an elastic elastic collision. All right, so our equation is going to look m1 v1 plus m2 v2 is equal to m1 v1 final plus m2 v2 final. So let's plug in what we know and solve for what we don't. So we have 4 kilograms times 0 plus 0.05 kilograms times 0. So our initial momentum for our system is 0 kilogram meters per second is equal to, we have 4 kilograms as our rocket, and we do not know the final velocity, plus the momentum of the fuel. So we have 0.05 kilograms times 625 meters per second. All right, so again, our initial momentum for our system is 0, so that means our final momentum for the system has to be equal to 0, just from the conservation of momentum. So let's go ahead and solve this stuff out. So we have 0.05 times 625, so that gives us a momentum of 31.25 kilogram meters per second. So in order to solve for V1F, I got to move this from both sides. So subtract by 31.25 from both sides. I'm going to be left with this negative 31.25 on my left side is equal to 4 kilograms times V1F. So I want to know what V1F is, so I'm going to divide by 4 kilograms on either side. This is going to be a negative velocity. So 31.25 divided by 4. So a negative 7.812 meters per second here. And you might be saying, Miss Brennan, if this thing is being shot off, why is this negative? And I would agree with you. It's because we set the fuel as positive. So if we set the fuel as negative, then we would get a positive velocity for our rocket. So you can go ahead and plug in negative 625 there, and you're going to find that you get the same velocity, just in the opposite direction. And that's because motion is all relative to your observer and your coordinate points. So the next one, you are at summer camp with your friend. Yay! You decide to take the canoe out for a trip around the lake. As you dock the canoe, your friend steps onto the dock with a velocity of 4 meters per second and a mass of 45 kilograms. You and the canoe have a combined mass of 110 kilograms. With what speed and direction does the canoe and you move? All right, so you're at summer camp and your friend decides to step out of the canoe from the lake to step on the dock. So I'm going to call your friend M1, and this has M1 has a mass of 45 kilograms, and they have a velocity of 4 meters per second. And you and the canoe have a combined mass of 110 kilograms. So this is 110 kilograms. And with what speed and what direction does the canoe and you move? So we have that initially this is at 0 meters per second. And the person that is stepping out is causing us to have a collision with the canoe. So this is actually going to be our final, and our initial is also going to be 0. So we want to solve for V2 final. Okay, so what type of collision is this? Well, it's an elastic collision, but it just deals with a combined mass of you and the canoe, so it makes it sound like it's an inelastic collision. But it's an elastic. Okay. All right, so let's start here. So we have M1 V1 plus M2 V2 is equal to M1 V1 final plus M2 V2 final. So let's plug in what we know. 45 kilograms times 0 plus 110 kilograms times 0 is equal to M1, which is 45, times 4, which is going to be our positive side, plus 110 kilograms times v2f, which we need to solve for. So again, our initial momentum total is going to be 0 meters per second. Okay, and we need to solve for this right side, or our final momentum, and we need it all to equal 0. So what does this final velocity have to be equal to? Let's find out. So we have 45 times 4, which is 180 kilogram meters per second, plus 110 kilograms times v2f. So in order to solve for v2f, we need to get it alone. So we should move this 180 from both sides. So we're going to have a minus here. And now we are left with our mass times our final velocity. So if we divide this out, our final velocity of u in the canoe is going to be negative 180 divided by 110, which is going to be negative 1.64 meters per second. Alright, so this is our last problem of the day. Sonia, a 45 kilogram ice skater, stands at rest on the ice after finishing her performance. A friend tosses her a 5 kilogram teddy bear. The skater and the ball, the bear, then move backwards across the ice with a speed of 0.5 meters per second. What was the initial speed of the teddy bear? So this is one of these examples where we have to use our conservation of momentum and our ideas of collision in order to solve for the initial speed or velocity of an object. So we start out the exact same way by recognizing that this is an inelastic collision because Sonia is going to catch the teddy bear. Okay, so our inelastic collision equation looks something like this. Our masses are going to combine. We're going to be left with a final velocity. Okay, so let's identify what we're given in the problem. So M1, I'm going to call Sonia, and she has a mass of 45 kilograms. And she's standing at rest on the ice after she finishes her performance, so V1 is going to be 0 meters per second. Okay. And a friend tosses her a teddy bear. So M2 is going to be the teddy bear, which is going to be 5 kilograms. And we are not sure what the initial velocity of the teddy bear was. That's what we need to solve for. And we can solve for it because we were given the final velocity of the teddy bear and Sonia together. And that was 0.5 meters per second. So we need to solve for what was this initial velocity that was throwing the teddy bear here. All right, so let's plug in what we know and solve for what we don't. So 45 times 0 plus 5 times v2. Again, that's what we're solving for. Plus 45 plus 5, just adding the masses here, times 0.5 meters per second, which was the final velocity for our momentum total final. All right, so this is going to be 0 plus 5 v2 is equal to 50 kilograms times 0.5 meters per second. So if we were to do that out, we would get 25. So 5 v2, and again that's kilograms, is equal to 25 kilogram meters per second. So our initial momentum has to equal our final momentum. So this initial velocity of the teddy bear is 5 meters per second. Okay, so I hope this was helpful to you. If you still have questions, please let me know.